Hi everyone, my name is Cagri. I'm one of the lead engineers in MySQL HeatWave team. Today I'm going to talk about MySQL HeatWave. Just before starting, I want to do a check. Who knows about HeatWave or heard about HeatWave? That's great. So, okay, so what was the motivation point for HeatWave, right? So when you look at this, the main point was, okay, we have the MySQL system for OLTP, it's great. You run transactions, we have seen the numbers, this is going better and better. But then when it comes to analytical queries, right, OLAP queries, you have very large tables, you have very big joins or group by queries and so on. And it's a little bit problematic, I would say, right? You try to run a TPCH or a TPCDS, then the performance is not that much promising. And what typically happens is you have the OLTP database, you extract your data and then put it into another database specialized for OLAP queries. And this is typically in the form of an ETL or an export and reingest into another database, very costly, slow, and tedious. That's the whole point or the main motivation behind HeatWave. Why don't put these two systems together and then you don't have to have this costly operation in between and answer both OLTP and OLAP queries from the same system. Here you can see an overall architecture or the end-to-end picture of how HeatWave looks like. We have the OLTP, MySQL, and HeatWave is integrated to it as a plugin or as a storage engine, so to say. And queries and results work as usual as expected. But behind the scenes, what we do is in addition to the MySQL server node, we have a cluster of compute nodes, right? And this can be in the number of tens or hundreds. Today we can go up to 512 nodes. And the system is really optimized for in-memory query processing. Your data is in memory, running multi-core. Today, I think in cloud, we are running with 32 threads in each of these. And what we do is we take your InnoDB data, for example, and offload it to in-memory representation to HeatWave. And then when your query comes, behind the scenes, we offload your query to this execution engine running on a cluster of compute nodes. Yeah, so I just realized MySQL is 30 years old. HeatWave is not that old, maybe order of magnitude younger than MySQL. But at the same time, I wanted to tell that this is a culmination of research, a lot of research that we were doing in Oracle Labs. That's why I wanted to give a little bit of a background so that it's clear for the people that it just didn't just appear, but there was a research behind. So yeah, we worked in Oracle Labs for many years and started as a system for software hardware co-design. Basically, even the chip was designed from scratch for Rapid. Back then, the project code name was Rapid. What we wanted to do is both power and performance efficiency. And in addition to hardware, the hardware was not the only key ingredient here. We also developed a scalable software design and architecture that can benefit from this hardware. To put it into a perspective, this was developed for thousands of compute nodes. These are all specialized DPU, like data processing, database processing units, really low power system on chip with specialized processing, specialized database instructions, and so on. And connected through a relatively expensive InfiniBand fabric. And at the top of the layer, you have the host database system. Back then, it was another database system. Yeah, I mean, so basically, this was the research and several publications have been made. You can find maybe more details if you're interested to see. This was published in Sigmod, one of the prime conferences in the database area. What we did is basically we dropped the hardware specialized part and took the software part and software enhancements and integrated it with MySQL, and then from then on the project HeatWave was. So how does it work? The query processing architecture is essentially same as MySQL, right? Users come with the same syntax and everything. And queries to the user doesn't matter whether it's coming from HeatWave or MySQL. But behind the scenes, as Norman also explained, we have tight integration into the SQL query compiler and the optimizer. We optimize those eligible queries to HeatWave and push them down to HeatWave execution. And on the HeatWave side, we do the necessary things for cluster management, cluster setup of the queries, scheduling the individual tasks, and then return back the results to MySQL, and from then it passes to the users. Now, what are the three fundamental pillars of HeatWave system? First of all, it's an in-memory system, so all your data is kept in memory. And it's hybrid columnar processing. So to contrast with MySQL, MySQL is a row store, meaning all the values in a row are stored one after another. In HeatWave, we slice the columns such that all the data that belongs to the same column are stored consecutively to each other. And pillar two is basically parallelism. We obtain the parallelism one through the massive inter-node parallelism. As I've shown, we can scale up to 512 nodes, compute nodes. This is a great scalability. And two, within each node, we carefully tune to that node. Meaning, if you have 32 physical CPU cores, you utilize them to do the scale up. And the third pillar is the query processing algorithms. Here we utilize some distributed query processing algorithms, which were back then, again, based on research and state of the art. So to detail a little bit more on the first pillar, the hybrid columnar processing side, what we have here is essentially, so think of it, this is your table, okay? So your columns and number of columns. We first have the horizontal scalability, meaning how do we distribute data across the compute nodes in your cluster. So we call the concept called partitioning, and each horizontal slice of your data is one partition, and we assign this to one compute node. Okay. Now, once we are within a compute node, we have the multi-core scalability. And how do we achieve that? We have a concept called chunking. A chunk is nothing but a slice of your data in the order of a few tens of megabytes. So each of these chunks are assigned to one processor core. Thereby, we achieve the parallelism across the CPU cores. Now, within CPU core, what happens? So we have the columns. This is an array of, in simplistic terms, array of values, right? And we further slice it down into vectors. Nothing to be or confused with the vectors that I will come to. But so this is, think of it an array, right? We slice it in such smaller pieces so that they typically fit in your cache. So if you're evaluating a filter condition, you can put it into your L1 cache, do one scan, and without any cache misses, you can do this processing very efficiently. So that is the vectorized execution. Now, when it comes to massive parallel architecture, I mean, I briefly touch upon these concepts, right? You have the partitions, so each compute node can work on each of these partitions. And within each core, you can have these chunks, and chunks are assigned to cores, so they independently, without any synchronization, they can work on those. So this is the essential, one of the essential ideas of rapid architecture, basically high fan-out, workload-aware partitioning. And machines and CPU cores can do the work in parallel. Okay, so the algorithms part. What is so special about HeatWave? First of all, we utilize partition throughout the system as a key optimization principle. This means we partition so fine granular that data fits into the cache. And once it is in cache, many things are much, much more efficient. Like today on commodity hardware, Intel or AMD, access to a single cache line is really in the single-digit latencies in terms of cycles. The second one is once the data is there, it enables in cache, it enables further optimizations. Like you can really write hardware-conscious code. You can use data parallelism, like through SIMD instructions, or even today in the latest generation AVX registers, which is like 512 bits of registers. You can pack essentially 16 32-bit integers and do the same operation on such elements in a parallel manner. And then the last one is more about the distribution and cluster network resources. What we do is we typically try to optimize for overlapping the compute intensive tasks with the communication. If we need to shuffle data across the compute nodes, we schedule in such a way that the CPU heavy tasks like hash calculation or compression, so to speak, can be overlapped with each other. So when you are doing CPU, you are issuing I/O, so then the latency between these two are hidden. I want to go a little bit of deeper here in terms of the algorithms. I mean, many of you probably know from the textbook hash join, right? Hash join, supposedly very simple algorithm, right? You build a hash table on one of the relations and then just probe it with the other side. But this is really the textbook one. Now, what we do differently in HeatWave? So we have the partitioning phase again here, right? If the data is not pre-partitioned, so that's another optimization. But let's assume data is not partitioned, so you can apply on-the-fly partitioning to your data to make sure resulting partitions fit into the CPU cache. And you do the same on the other side. You partition that too. And then you end up with very small partition pairs. This is in the order of at most few megabytes. And we typically even want to reduce it to the L1 cache size, let's say 64 kilobytes or so. And once this is in there, you build a hash table on this small relation, not the bigger one, and probe that with the corresponding probe relation. So all of these operations will be in cache, right? Building the hash table, everything is in cache, and probing it through the cache. So no memory round trips when you are executing this join kernel.
Just one question, it's not clear. Let's suppose on your last chunk you have a hash. How do you know that this hash will not match with a chunk that is another CPU?
I mean, what you see here is what is happening on one machine, right? But before this, or you can take this P, right? If P is too large, then there is another phase, another cluster level distribution. Actually, this figure shows it, right? So if your data is on different nodes, you have this, what we call system partitioning. Basically, using the same hash function, you first shuffle your data across the cluster compute nodes. So whatever you shuffle, you are sure that the resulting partitions after system partitioning end up in the same compute node. Now, after that, once you are within the compute node, then you execute the algorithm that I just showed, and everything now is on the same machine. And so then it raises the question, how much partitioning we do really need to do, right? It really depends. Again, there are some calculations behind it. As I said, we want to make sure that, okay, so let's say we do not do any partitioning. What happens? You have the hash table, and then you are probing this. So this is, if this is like a few gigs, which means you are doing a random access to some memory location, and every access becomes a cache line miss. And even further, it becomes, okay, I'll come to that, but the first thing is cache miss, right? Then how do we use the sizing such that it fits into the cache? So L1 cache is 64 kilobytes today, and L3 cache 4 to 8 megabytes, depending on the architecture that you are using. So if you do some math, you end up, and this example is really for TPCH 10 terabyte, I believe. For this scale of data, you need 134 million partitions. And how we do achieve it? We first do cluster level partitioning, and then within nodes, we do further another round of partitioning. And this way, multi-round of partitioning, we end up with these smaller sized partitions. So, okay, another problem. You are doing the partitioning, right? Partitioning may be depicted with a very small, simple pseudocode here. You hash it, and then you try to write into some partitions, right? But even here, P is a random number, right? And if this is high, what happens is you end up with translation look-aside buffer misses. So this is even more costlier than a cache miss. So just a recap, this is from Computer Architecture 101. This is a small cache in your processor that does the virtual to physical page mappings. So it's really another cache, so to speak. And then the cost of this is way more, because if you have a miss in the TLB, it means you have to walk through a tree of pages and then figure out, okay, for this virtual address, where is my physical address, and so on and so forth. So this is why we want to avoid very high partitioning fan-out as well. And based on experiments, we understood this is a problem, right? If you go beyond certain partitioning fan-out, this causes a lot of TLB misses. And what is the solution? Solution is again depicted here in a simple pseudocode. So what you do is essentially you maintain a smaller cache line size buffer per partition, and you buffer the writes there, right? So let's say, and this technique is called software managed buffers. You write a number of records in a cache line, and once the cache line is full, you say, okay, I'm flushing this cache line to memory. So this way you reduce the pressure on the TLB. And with that, you can end up going up to 2K partitions without incurring significant overhead on the processor. Okay. So I'm switching over to a few other optimizations we follow. One of them is memory conscious processing. So, okay, we are an in-memory system, but memory is still a scarce resource. So what do we do? Here on the left side, you see a query plan, and these are designated as number of operators like table scan, join build, join probe, and some expression evaluator, and maybe some selection and so on. So what might the executor choose is take one of these, execute, write the result back to memory, and then when the next one comes, takes the data from memory, runs what it is supposed to do, and then write the result into memory, and so on and so forth. So basically, pipelining through writing in blocks to memory, right? But what we wanted to achieve is a little bit different. There is an opportunity in many of the query trees to pipeline things. Not always, because between certain operators you cannot do pipelining, but between some, for example, build and probe, you can do pipelining. So you write a limited number of rows here, and then take those for using in the next operator. And for example, from the join result, you write a number of rows, output into a small buffer, and then take the next operator and then execute from there. So this way, you can avoid full materialization to the memory, and you can reduce the memory pressure. Another improvement that we are utilizing is, this is again in the query plan improvement. The optimizer learns and improves itself over the course of time. How does it happen? So we run one query, it's naive, it doesn't know anything about it. Maybe the query performance is not that good. That's fine, but what we do is we cache the cardinality estimates of subtrees, not the entire tree, or we do not materialize anything, but we just cache, okay, A and B join was resulting in this much cardinality, this many number of rows. Or table scan was resulting in this many number of rows, and so on, right? We cache all the things that we see. And then maybe next time around we are lucky, if the same query comes, we know all the statistics perfectly, so the next time it will run really great. But let's say we are not lucky, but we see A-B join, or parts of the query, or maybe a more larger query that can utilize this as a subtree, then we can plug in all these statistics there, and this way we can make really perfect choices in the optimizer level.
Just a quick question. So this information gets fed back into the optimizer.
Yes.
And what Norval was talking about earlier,
yes.
even in the NODB, the information
yes.
in theory can go back, and therefore the
Absolutely.
second file
Absolutely.
it will do things differently because it's more aware of the place.
That's exactly what we do. we have tightly integrated with Hypergraph Optimizer. Now, the first time, as I said, okay, for table scans and so on, in HeatWave we have good statistics. But for intermediate joins and so on, we may not.
Yeah.
So the first time we cache those or keep those in statistics, and then we feed in the next optimization for the hypergraph, and we get the perfect blend essentially.
So it's also already workloads, or just only workloads or also
Any query that can benefit HeatWave. I mean, okay, there are types of queries which will not run that, okay, it will run fast, but InnoDB is still prefers, like, what is it, like point lookups or point updates. This is not the system for that, but except those, I mean, any query will benefit from this. Okay, yeah, this is exactly, I think, we are just going ahead of the slides. This is how we integrate it into the Hypergraph Optimizer, right? I mean, we use Hypergraph that Norval spoke about. And as we gather more statistics, we feed these statistics back into the Hypergraph Optimizer. And then, therefore, basically, cardinality stats or cost models, and this will be perfect. This one I explain. So, putting all together, I mean, okay, I'm a little bit. Yeah, I don't want to show too many performance numbers, and we have a lot of public numbers. They are available in GitHub and so on. We compare with competitors and so on. I don't want to sound like a marketing, but here I just want to show some numbers that we obtained running standard TPCH on 400 gigabytes on a single machine, right? And we are just comparing this with MySQL here on the slide, since this is a MySQL forum. You can see mileage may vary, but geometric mean we are about 400 times faster than MySQL industries for the TPCH. All right, so with that, I'm already in my conclusion slide. What I described is some architectural background on HeatWave with the design choices we made and how we wanted to optimize the system for analytical queries. And at the same time, arriving in a single system which both caters OLTP and analytics applications. And I emphasize that we do not require any SQL change. It should continue if you have an existing MySQL application, a set of queries, they should work seamlessly. And then I showed that all of queries, we have a good performance improvement and scalability, and cost-wise, that's another dimension. So I guess that's the end of my, if there are questions.
So, from what I understood, there is no like, if you start the database, like how your statistics and query plans goes down. Like it disappears. So you need to warm up the database every time you start. The queries need to get into the pipeline.
That's not exactly true. The parts which I have not described is when we load a table to HeatWave, we generate these statistics during this phase, right? And we, by the way, generate extensive amount of statistics like number of distinct values, max values, histograms, so to speak. And then we write these to object storage. We take a snapshot of those. So, and we can basically utilize that.
I mean, more similar, I think Oracle database is doing it like you can bind the query plan to that specific query. Like, do you guys have a plan or something to do this?
No, we do not memorize query plans or anything, but we memorize the statistics, whatever we have seen, right? Then it's sort of a pattern matching, or you receive a new query. Okay, from the statistics that I have seen or the execution subgraphs I've seen, how can I match to this new query? And we try to do that. So we do not fully memorize the entire query or the entire plan.
Excuse me, can you just get back 3 slides, please? Yes, please. So here's the Hyper optimizer and the HeatWave optimizer. When we do the correlations, when you guys do the correlation?
So the hypergraph optimizer, I don't know if you were in the previous talk, it takes the join tree, does the generic optimization and so on, and then it asks the storage engine for each table, okay, what is the best way to access this table, right? InnoDB may say, okay, it's an index lookup, and here's my cost. And then when it comes to HeatWave, they ask, okay, what is your strategy? And we say, okay, it's a table scan, and we can scan it in this much of time, and we expect this many number of rows, right?
Okay, so you do this when the HeatWave system is up and running, or
Yes.
before the HeatWave, if the table is not
HeatWave
loaded?
system must be up and running, and
Okay.
its cloud is owned by default.
Okay.
And then the logic, like we end up the plan. But there is the another step. Let's say if MySQL Optimizer, Hypergraph Optimizer chooses HeatWave, then we do another pass over that plan and then generate a physical plan. Okay, I need to place these joins on these compute nodes. I need to push the maybe group by aggregation here and there. So we really do physical optimization and end up with a bit more complicated physical operating place.
I wanted to say maybe there is some row missing there or number, and also to answer what Vinny was asking. The thing is that the plan of HeatWave, it's not always selected, right, by default. So for example, you say, oh, if you save it, but maybe you will never get there because to access HeatWave, or you force it, or you just, the first time is the optimizer that tells you, oh, this is my query, optimizer said, this is the cost. If the cost is very low, it will never, even if you have HeatWave enabled, it will not get there, right? So here, there is first always the optimizer. So if you want to save query plans, it should be implemented in the MySQL optimizer first, I would say, so MySQL can say, oh, it's in InnoDB Go or whatever, and then, or it goes to HeatWave, and then in HeatWave, find a way to find the saved plan also, right? So it always go to MySQL optimizer, and depending of the cost, it would go to say, okay, run this query to HeatWave because it's much faster. So that's the thing. So there is I think it always go to optimizer, and depending on the threshold that you can modify if you want, but this is
You can force to this choice basically. You can say you always go to HeatWave, but we let it to the optimizer to decide. Because that's really the best.
Could you make sure that the data is synchronized?
Okay, good point. I think I have not covered it. We are relying on binlog, but we internally implemented essentially binlog listener, so to speak, high performance multi-threaded in C++, and we collect these and then ship to and it's a delta update, I would say. It's not really a full blown.
And is it consistent?
It's consistent with snapshot evaluation.
So there can be issues with long DBL, for example. If you reveal the table in
Yeah, I mean, so the thing is, this is, I think, on the OLTP side, right? If you're inserting 1 million rows, then yeah, probably there is going to be some blocking.
or you change the tolerance.
Yeah, I mean, in such a case, what we noticed is instead of incremental updates, probably it's a reload is much faster operation than HeatWave.
But if you do a DDL, you need to disable, I think still now the HeatWave. So you do your DDL and then you need to reload it. The reload is very fast, but there is you cannot modify online a table while it's loaded.
I mean, you can insert rows, that's no problem. But if you do a full DDL, yes, probably that means.
It's a difficult problem.
Are there any delays in the binlog getting applied to being good? That's asynchronous. You're reading it right now.
Yeah, it is synchronous. We have to wait for the changes for the snapshot isolation. We have to wait changes to be propagated, and then only then we allow queries to continue. Here's some log we get, but typically, I mean, if the transactions are not really doing a full change of the entire table, that's usually good.
Makes sense.
So, do you have a way of tuning the feedback loop? The feedback loop between the HeatWave optimizer and Hypergraph optimizer. Do you have a way of tuning? Like if you're seeing that the feedback that you are giving is not getting the results that you're expecting.
Okay, the feedback loop is per query, right?
Yeah.
You run the query, you get the feedback from HeatWave statistics and so on, you run it, and then you saw that, okay, well, this time the query didn't went well, and that one will be cached instead of the previous one. So the next time you run, you will run with more updated or better statistics or better data. Within the same query, no, but in the next query, you will have the updated information.
Okay, so you have said that it's always better. Like there is no regression, there is no.
Yes.
Okay.
Thank you very much.